Here are our solutions to homework set number 8 for ECE 463 Modern Control. This homework looks at linear observers. Now, the first problem is take a cart and pendulum system. Get an idea what that looks like is this. There we are. What I want to do is come up with a full order observer where just measure cart position and then come up with a full order observer to estimate the states, and then given the states, control the system. So if I do nothing, it falls over. So first I need to find a feedback control law that stabilizes it. From the observer standpoint, I don't really care. Whatever the input is, however you calculate it, whatever you apply to the plant, apply the same thing to the observer. But it simulates a lot better if it doesn't fall over. So that's the first part. Come up with a feedback control law that stabilizes it. And I did change the homework just because the dynamics that I gave you previously were wrong. So when you design the observer doesn't work. The observer needs the correct dynamics, not the wrong dynamics. So these are the correct dynamics for the nonlinear system. First problem is come up with a stabilizing feedback control law. And in this one, you're asked to come up with it in this form, full state feedback with an input gain such that I get 2% overshoot for your 2% settling time of 8 seconds, 5% overshoot. That puts the dominant poles at minus 0.5 plus minus j 0.525. So given the A matrix, B matrix, use Bhaskara or pole placement to place the dominant poles. The other two poles don't really matter. When you're done, you get your feedback gain Kx. Then find the gain Kr to make the DC gain 1. Now if I do that and plot the step response to the closed loop system, so there's the closed loop A matrix, B matrix, C and D don't change. Take the step response and it should work. I've got about 5% overshoot, 8 second settling time, ballpark. DC gains 1. This undershoot is just how the cart behaves. I've got to go the wrong direction to get it to lean, to move in the right direction. Just how it behaves. That's the nonlinear system. Now design a full order observer. Again, where you put the poles is kind of arbitrary. I chose it 2 to 5 times faster. For the open loop system, the dominant pole is at minus 0.5. So here I put the dominant pole at minus 2. And the other 3 poles someplace stable. I just chose 3, 4, 5. Plug that in, you get your observer gain H. And checking, the observer gain is in the right spot. Now, let's see if it works. Let's use full state feedback from problem 2 with a full order observer and see, does the observer track the plant? So when I come up with the closed loop system, in this case, is now 8th order, 4 poles for the plant, 4 poles for the observer. X dot equals AX plus B times minus KX times X. So there's your A minus BKX. That covers X dot plus BKRR. The observer's state, XE dot, is A, I got this the wrong spot, minus H times C times XE plus B times KR plus B times minus Kx times X. So there's the state space model when I feedback the plant states. If I try that, so here's your 8 by 8 A matrix, there's A minus BKX, A minus 8C, and this is 8C minus BKX. Checking the eigenvalues are the poles of the observer and the poles of the plant. Again, that's the separation principle. The observer and full state feedback don't interact. Pick KR to make the, whatever I do to the plant, do the same thing to the observer. And here I'm going to look at the plant's output and the observer output. For the initial condition, here's the plant, observer. If they start with different initial conditions, take the step response. And here I need to use the step 3 because I have my initial conditions right here. That's the function that we wrote last week. So here's the closed loop A system, A matrix. It's now 8 by 8. B matrix with respect to R, C and D. Take the step response. And initially it's a little bit off. That's because the observer states are wrong in 4/3 of a second. Since the observer poles at minus 3, 4/3 of a second, the observer tracks, and it tracks the plant. And if you try that with a nonlinear system, just kind of for fun, there we are. Okay, so here's the full state feedback from before. Here's my plant model. It's important to have the correct model for the system. Find H to place the poles at minus 3, 4, 5, 6. Now I want to simulate it. Whatever I do to U, this is how I find U. U applies to the actual cart and applies to the observer. In addition, I feedback H times the difference between the actual output and the estimated output. Integrate the plant, integrate the observer, and here I'm feeding back the actual states. Now if the observer states are a little bit wrong, let's just move it over by 0.1. So the initial observer is 0.1 off in position. Here's what she looks like. Again, I'm feeding back the actual states so it'll be stable. The observer ought to track, and the observer is in magenta. And C, initially, this is a little bit different. Fairly quickly, it starts to track. Once the observer error is driven to 0, it remains small. It's not exactly 0 because the plant has dynamics the observer doesn't take into account, like the Coriolis forces, the nonlinear terms. But the feedback says whatever those errors are or disturbances are, those effects are quickly driven to 0. So this is behaving pretty well. I want to make it behave a little bit bigger. Let's try that. Initially a bigger starting transient, but pretty quickly converges. Let's see, going on to problem 4. Now this is really the whole point behind the observer. I don't know what the states are, but I can measure the output position. From that, estimate the states. Since I don't know what the states are, I can't feed them back because I don't know what they are, but I can estimate them. So instead of feeding back the actual state, feed back the observer states. So this is now gone. Here's the actual block diagram. That gives you this state space model. So like for the observer, I've got XC dot is AXE, got this minus sign in the wrong spot, minus HC times X plus HC times X, or HC times X, minus HC times XE, minus BKX times XE. So there's the closed loop system when I feed back the estimated states. If I try that in MATLAB using the linear model, I'm going to have to put the matrices in the right spot. Let's see. Take the step response with initial conditions on x0, and you get a kind of wild initial step response. That's just because the observer states are wrong. When I feed back wrong gains, wrong estimates, I get kind of a wild response, but eventually it does converge. If you make the initial error 0, I get a nice clean step response. So that's for the linear system. For the nonlinear system, what I do is just that change right there. If instead of feeding back the actual states, I feed back the estimated states, now the only thing I'm using is the measurement of position. That estimates the states that are then used to find the feedback control law. If the error is initially 0, I get this response. Here you've got two outputs. The red is the plant, the pink is the observer, and you can't really tell the difference just because it's working, it's tracking. So that's the ideal situation. Once the observer states converge, it works actually really well. And we'll let it settle out. Now, if there's a slight error, in the initial states, it behaves kind of wild that first time. That's because for the first 4/3 of a second, the observer is trying to track, trying to figure out what the states are. During that first 4/3 of a second, the response is kind of erratic. Once the observer states converge, like the second step, it works very well. But again, you got to have the right dynamics for the observer. If the dynamics are wrong, your data estimates are wrong. Yeah, it basically doesn't work real well. So that is homework set number 8 for 463, full order observers.